Okay, cool. Let's start. So my name is Jose Nino, and I work at Lyft. And today we're going to talk a little bit about Envoy at Lyft. So I am an Envoy maintainer, and I also work in the networking team at Lyft. That means that I'm in a pretty interesting spot because I helped create Envoy and now maintain it, but I also need to operate it at scale in the Lyft engineering org. So a little bit about my time at Lyft. I actually started a couple months before we open sourced Envoy, and one of my first tasks was to actually sit down and read the entire documentation to make sure it made sense to a newcomer. So if you've read some of that, I helped edit a lot of it. Then after that, I work on creating a cluster at Envoy. Lyft created called Envoy Outbound that enable developers to communicate with external partners over stable IPs. This is a problem that at Lyft before was heterogeneous, and everyone was rolling out their own bespoke systems. But with Envoy, we were able to homogenize that experience for all of our developers. After that, I worked on open sourcing rate limit, which is Lyft's version of a rate limit service. It's written in Go, and with it, I also open sourced a couple other libraries. And in addition to writing the production code, I also wrote a ton of documentation to make sure that everyone knew how to use it. After that, I worked on expanding Envoy's outlier detection system in order to allow service developers to know where anomalies were happening in their own clusters. And for the past couple of quarters, I've been really revamping Lyft's configuration management system for Envoy. And so that's going to be a good chunk of this talk. So why am I telling you all this? It's not just because I like talking about myself, but there's actually a pattern here. And the pattern is the focus is on developer productivity. The story I want to tell today, other than introducing Envoy, is that I hope to prove that Envoy is a powerful and complex tool, but really the focus here for the networking team at Lyft is to hide the complexity of Envoy to allow service developers to actually go and write the business logic that Lyft cares about. So why is this important? It's important because at Lyft, we believe that infrastructure engineers are indebted to the rest of the engineering org. The rest of the engineering org is our customer, and if we ask them to produce beautiful and easy-to-use products, then we should do the same for them. In addition, Lyft is growing like crazy, so we're going to have a lot more hands on deck. By the end of the year, we presume to double our engineering org, which will bring us to over 1,000 engineers. So this means that the complexity of our system will increase. We have a microservice architecture, and so that means that with more engineers, more minds, more hands, more services. And so our distributed system is going to be more complex. How can we hide that from our service developers? So the frame of reference I'm going to use today to talk about hiding complexity is configuration management, because proxy configuration is really complicated, and Envoy is really no exception. With a full production rollout, like I'm going to describe in a couple of minutes, you can end up with thousands of lines of JSON or YAML if you prefer that. But this is complicated, and really configuring the data plane should be reserved to a select few. For example, the networking team at Lyft. But we should open up the data plane to be manipulated via the control plane to our service developers. If they want to create new routes, new services, we should allow them to have the tools to do that. So before I get to configuration management and how we hide complexity, I want to touch a little bit about Envoy itself, and given this is an intro talk. So Envoy is a networking proxy. It's out of process architecture. This means that it is not a library that service developers import. It sits as a different process in your host. And this gives us two very important things. One, we don't need to rewrite it for every single language we support at Lyft. Lyft is a polyglot company, so we have Go and Python, PHP, and some Java. And in addition, because it's not a library, we can roll it out whenever we want. That means that we don't need to core service engineers to upgrade their library every time we write something new. We just deploy a new binary out to the entire service mesh. Envoy was written with low latency and high throughput in mind, but without compromising on developer productivity, both in the code base and also in the ergonomics of using Envoy. It has a very rich filter architecture, so if you've used something like Netty before, Envoy defines filters that you can stack to create complex and rich networking pipelines, both at the L3 and L4 layer and app at the L7 layer. Envoy was also designed with HTTP2 in mind as a first-class citizen. It's only until recently that other proxies, like, for example, Nginx, have caught up and supported HTTP2. But we knew that from the beginning that it was going to be important to design Envoy with HTTP2 in mind as a first-class citizen. And we also have a very rich service and discovery system, and also config discovery system, and that's what I'm going to focus on the latter half of this talk. It has active and passive health checking, so you can, as I said before, detect anomalies in your clusters and inject hosts in a dynamic way. Of course, it's a proxy, so you have to load balance stuff. And it's also designed as with deploying Envoy everywhere in mind. So that means that you operate the same proxy at the edge of your infrastructure and your service mesh. We used to see in the past where people would deploy, for example, Nginx at the edge and then HA proxy in the mesh. But operationally, this becomes very taxing for the team that operates that. And perhaps the most important goal of Envoy is best-in-class observability. It is our goal to make the network transparency to our service developers, and if we don't provide them the stats, the logging, and the tracing that they need to do that, then we failed. So how do we roll out this at Lyft? It actually started first at the edge. If you went to Mark McBride's talk yesterday about migrations, he would tell you that migrations are a very social activity, and you have to prove value very quickly, especially in a migration of this scale. So by putting Envoy at the edge, we were able to provide a lot of value really quickly by enhanced load balancing at the edge, statistics, routing, and supporting multiple protocols. After we deployed at the edge, we went and put it in every single service to do Mongo routing. So first, it was able to parse Mongo at the L7 layer and get useful stats. Again, best-in-class observability. But more importantly, it had better connection handling to raw Mongo. So it proved value very quickly. After we did our Mongo rollout, we went and did the service Sidecar. So the benefit of having rolled out Mongo is that Envoy actually ran on every service at Lyft already. So at that point, the price was paid. And then, again, we started providing service owners with a lot of value by doing ingress breaking or circuit breaking and doing a lot of observability as well. So the natural evolution after that was service mesh. Actually take out the AWS ELBs in between services and let Envoy to Envoy communicate across the network. And this was enabled by providing a service discovery, which is at Lyft is very simple. We don't use Zookeeper or Console or anything like that. It's just a job that runs on every single service, registering with our discovery service, and then our discovery service fans that information out to every Envoy in the mesh. So that brings us to today. So where is Envoy today at Lyft? It's everywhere. And that was one of our design goals from the beginning. So right now, Lyft runs over 200 services with over 20,000 hosts and about, at peak, 5 million RPS in the mesh. We have Envoy, as I said, at the edge, inside all of our services, and also to use with communication out of our infrastructure. In addition, we have a couple ancillary services to Envoy, our tracing collectors, rate limit, as I explained before, and our discovery service. OK, so that's how we rolled out Envoy. Now, how do we operate it? and how do we operate it with, how do we operate its configuration? So in the past, when we were rolling out Envoy, we started out very simple. There was a human, and that human edited static files. Then we had some deploy magic, and that put configuration files out into our proxies. There were only two types of configurations, at the edge and in our sidecars, and it was deployed together with code changes to the proxies. So when you were deploying configuration, you were also deploying binary changes. As we scaled and we deployed out to the mesh, it became clear that we had to provide more fine-tuning for service owners. So we created a bespoke templating system that used Jinja 2 and Python to merge things that service developers were cared about, so circuit breaking or retries or routing policies, with data plane configuration that only the networking team manipulated. But again, this process was really complex. So for example, let's use a use case here of having a new public route at Lyft. Service developers would go into giant JSON files that had the entirety of Lyft's public routing policies. Then they would make changes to that and submit those changes as PRs to the networking team. Then the networking team would review them and take them out with an Envoy deploy. What were the pain points that we saw with this system at Lyft? Well, first, there's no clear ownership. The service developer is making changes to configuration, but after the configuration changes merge into master, the networking team is taking out that configuration. And that means that configuration deployments are tied to binary deployments, which really doesn't scale at Lyft, and I'm assuming companies of the same size, because the velocity of deploying Envoy at Lyft should not be the same of deploying 200 microservices at any company. That means that while we want to deploy our services dozens and maybe even hundreds of times a day, we don't want to deploy Envoy every time that happens. So that means that the user experience for our service developers is fragmented. They're used to high throughput and high velocity of changes in their service, but they really can't affect the network at the same speed. So where did that put us? In the middle of 2017, Envoy created a set of APIs called the XDS APIs. And this is a family of APIs for configuration management. So you might imagine we have route discovery service, cluster discovery service, listener discovery service, etc., so that a configuration service can provide these types of artifacts out to service proxies dynamically. This set of APIs are gRPC and protobuf based. That means that we have strong type contracts between configuration artifacts and Envoy. It supports bidirectional gRPC streaming, and it allows us to interact with the control plane separate from the data plane. This means that we can start writing robust and resilient control planes that are separate from the data plane. So what did we do at Lyft? We built this. So let me break it down. In the left, we have what service developers interact with. So for example, for the use case that I was explaining before, you might imagine a service developer wants to create a new public route. So they would go into their public route configuration and create a new route that has, for example, a match with a path, and then it points to their specific service. In addition, you also want to configure the service mesh. So every single service at Lyft has a manifest, which hosts a plethora of configuration. And within that configuration, there's also Envoy configuration. So a snippet of Envoy configuration in this manifest might look like this, where you define, for example, internal services at Lyft, roads, locations, ETA, external services that your particular service might communicate to, like Kinesis or Dynamo, and also other important aspects of the control plane that we want to expose to service developers. So for example, again, circuit breakers, max retries, shadow traffic. After the service developer has made these configuration changes and merged them into master, they can deploy them just like they would deploy their own code. So that means that the experience is really not fragmented. This configuration ends up in a blob storage, so AWS S3 or Google's cloud storage. It's really agnostic. And then comes the meat of this new configuration management system, which is Envoy Manager. And Envoy Manager really is a service that comes in 3 parts. The first part is data processing. So this is the cycle that picks up configuration changes and then translate them into actual XDS artifacts. So it might take the configuration of a new public route and put it into an RDS object. Or it might take a new cluster circuit breaker and put it into the cluster definition in cluster discovery service. Then after the configuration is generated, it goes into a caching layer. And then after that, it is served to all the proxies via an XDS server that knows how to speak the gRPC streams that I was describing before. So again, this is the entire diagram. So Envoy Manager really fits in the Envoy ecosystem at Lyft, just like any of the other ancillary services that we have. It sits in our infrastructure and it informs Envoy of all the dynamic configuration that it knows about. So how did this new process hide the complexity that we were seeing before? So let's revisit again the use case of creating a new public route at Lyft. It actually starts with documentation. In the networking team, we really value documentation. This is clear from the public Envoy docs, but it also is rich internally. So on top of those public Envoy route docs, we have created a good set of documentation to allow our service developers to iterate very quickly. So we've built step-by-step guides on how to do everything. We've written FAQs, and we've even experimented with some videos. So what does making a change look like? A service developer makes a change, and then they submit it just like a code change. A config change looks exactly like a code change. The service developer makes a PR. The PR gets reviewed by their teammates. And in this PR, we also have continuous integration that validates that new configuration is gonna be successful. Deployment, as I was saying, looks exactly the same as code deployment at Lyft. We use Slack to initiate deployment jobs. So here you see a service developer, me, deploying some configuration. The service engineer can initiate the job and see the payload of that job. And so it uses the same mechanics. So there's really no fragmentation in the process for deploying code changes and deploying configuration changes. And once the deployment has started, the deployment pipeline looks exactly the same for configuration as it does for code. Configuration goes through the same stages as code would go, so you can validate in staging and Canary, and then in production that your configuration change is successful. On top of that, we have leveraged Git as our versioning system for configuration. So if you went to Alexis' session yesterday on GitOps, this really is the same. We treat configuration just as we treat code. It's version control. This means that there's semantic versions attached to every configuration change for Envoy at Lyft. This allows us to leverage monitoring throughout the entire pipeline. Service developers are not confused about the configuration that is in production or staging or Canary. And more importantly, it's easy to roll back and roll forward. You just revert a commit, deploy that new change. Additionally, we provide rich monitoring for every configuration change at Lyft. So for example, this is a Grafana dashboard for Envoy Manager. And so when Envoy Manager is creating new configuration artifacts, you can see that versioning that I was speaking about before changing as the service developer is deploying in each stage. Additionally, we have dashboards, of course, in front Envoy. So for the example that I was talking about before with a new public route, you might be interested in the level of 400s that you're seeing as you're deploying a new route. And lastly, every single service at Lyft gets a dashboard for free with a bunch of macros that show a lot of the networking layer. So here, what might be important is that if you're creating a new public route for your service, you want to see traffic hitting into the service as the configuration is rolled out. So what are the wins with this new system? Well, we allow service developers to own configuration changes end-to-end. That means that the service developer has a new feature, they want to create a new route, they make the change, make the PR, get reviewed, deploy, monitor, everything. The networking team has no influence in those changes. Most configuration changes do not entail an Envoy restart. And more importantly, most configuration changes don't entail an Envoy binary deployment. This is important because as I was talking before, the velocity of configuration changes for the control plane is much higher than the velocity of deployments for Envoy code changes. So it's important to allow service developers to move as fast as possible without compromising the reliability of our system. And lastly, it really opens up the world to more friendly user interfaces and user experiences for our service developers. They don't need to touch giant JSON blobs, but they can make really specific changes into the system. So what does this look like in the future? In the future, it might be that we allow our service developers to have a web app that they can log into and create new routes via a friendly user interface. This actually comes from a company called Turbine Labs, which is providing some of the services. So in summary, what I want to leave you with is that while the networking team does create and maintain Envoy, it really focuses on accessible and easy-to-use systems for service developers to configure, operate, and then debug Envoy at scale. That's it for me. Thank you very much. And I think we have some time for questions, right? OK.
Yeah. OK, when I look at the Envoy manager as taking a high-level YAML from a developer and pushing the configuration into the Envoy, it really looks like the pilot component of Istio.
Yeah. Do you want me to comment on it?
Yeah, because you are part of Istio as well, and it lacks a double development.
Yeah. So let me actually first clarify that the Envoy project and Istio, Istio uses Envoy as their proxy layer, right? Like you can use Envoy and you can use Istio, and at Lyft, for example, we carry the baggage of having created Envoy, so we carry 3 years of Envoy, and so it's not easy for us to just go ahead and say, okay, let's scrap all of this and go use Istio. First, second, Istio does not provide all the capabilities that we use Envoy for at Lyft, and it also provides us using naked Envoy provides us with the flexibility of doing what we need at Lyft. The third point I want to make is that configuration management, as I said, and I like this slide a lot, really comes as a service in 3 parts, right? So you might imagine that the XDS server part and the caching layer are really company agnostic. And in fact, if you look at the Envoy project, we have a project within it called Go Control Plane, and it's mirrored in Java Control Plane, which has written as a library the caching and the XDS server layer. So that's how we're trying to minimize duplication. But really, the part at the left, the data processing, is really company specific. So if you go into the Envoy manager code, while these two layers are really open sourceable, the data processing part is company specific and really not easy to made abstract. Because again, most companies come into this with a lot of preconceived notions and preconceived abstractions that they use. So that's my take on it. Mm-hmm. Anyone else? I also have meet the maintainers from 12:30 to 1:30 if anyone wants to speak afterwards. Yep.
Are the three Envoy layers, the front, mesh, and what was it, out?
Mm-hmm.
How independent are they?
Do you mean in terms of like deploying code or configuration or?
Yeah, so they share the Envoy manager control. Do they share anything else?
Yeah. So they do share the Envoy Manager control. Envoy Manager, in its caching layer, knows how to speak resources to every single Envoy in our fleet. They also share a deployment strategy. So when we deploy Envoy code changes at Lyft in regular trains twice a week, and when we're deploying Envoy changes, we actually deploy to the front first, because as a networking team, we own that cluster, and it's easy to detect if this deployment is creating conflicts. Then after we deploy the front, we go and deploy what we call base, and that's the entirety of the mesh. So we're hot restarting, in stages, of course, but we're hot restarting the entire mesh with new binaries. Mm-hmm. Yeah.
You are primarily making a proxy, so the question is, are you dealing with legacy applications that are using sticky sessions, for example?
Yeah. So
I read something on the GitHub, and there are some issues regarding this question. For instance, I knew you are doing the hashing of the headers, for
yeah.
example.
Mm-hmm.
You have to investigate the application at some point, and therefore, how it is possible to transparently put in the proxy as edge proxy and manage it.
Yeah, so I think that's a topic that is ongoing. What Envoy has done up until now is have consistent load balancing, consistent hashing load balancing, so that then you can start building for like sticky sessions and things like that. But yeah, that's an ongoing effort. Mhm.
Which kind of systems this runs on? Like I can run Kubernetes or bare metal VMs?
Yeah, all of it. So you can compile an Envoy binary and plop it in whatever deployment ecosystem that you have.
Right.
Mhm. All right, I think that's it. I need to run to my other session. Thank you very much.